for the all pair shortest path problem. We have already seen in the previous class how can we solve the all pair shortest path in a graph, and we already know a solution of n cube log n using matrix multiplication, and also using Dijkstra repeatedly we can have something like n square log n plus mn log n, right, which can be in the worst case n cube log n again. But Dijkstra's repeated algorithm does not work for graphs which may have negative weights, but matrix multiplication algorithm that will always work for any graph with any weights. So today this Floyd Warshall's algorithm will see it works for any graphs with negative weights also, and the complexity is not n cube log n, it is n cube. Now, before I give you the Floyd Warshall's algorithm for the shortest path problem, I will use this algorithm for another problem which is very much related to the shortest path problem, which is called the transitive closure of a graph. So what is a transitive closure? The definition is this: compute, I am saying it compute, but in terms of definition I should not say compute, but you can always define this way. So definition of this is compute this: Dij is equal to 1 if there exists a path from I to j, otherwise 0 otherwise. So if you compute this matrix Dij, this basically computes the transitive closure of the graph, given graph. So what does it mean? You are creating as if a new graph from the given graph, where two vertices in the vertex set is the same as the previous vertex set of the graph. Only thing is, if between any two vertices there is a path, not only merely an edge, suppose there is a path, then you will introduce an edge between these two vertices in the new graph. So for example, suppose I do this. So this is 1, I am indexing them with integers. From now on we will see the vertices are indexed by integers. So suppose this is a graph, taking a directed graph here. Now for this graph, you can see there is no edge from 1 to 3. But in the transitive closure, there will be an edge from 1 to 3 because there is a path from 1 to 3, 1, 2, 3. So D13 should be 1. Similarly, there is no path, no edge from 1 to say 5. But in the transitive closure, there would not also be any edge between 1 to 5 because there does not exist any path between 1 to 5, from 1 to 5. So whenever there is a path between two vertices in the transitive closure of the graph, you draw an edge between these two vertices. So you will get a new graph basically from this if you draw. So keep this example in mind. We will see how Floyd Warshall's algorithm can compute a transitive closure for this graph later. Now, the Floyd Warshall's algorithm, the strategy is very simple. Strategy is this: yes, algorithm computes the matrix D. Computes D. How? It has several iterations. At the kth iteration, so this is the invariant. At the kth iteration of the algorithm, we set Dij is equal to 1 for any ij if there is a path from I to j that goes through all vertices with indices less than equal to, or I am just putting it less than equal to k except the two endpoints I and j. So this is the invariant of the algorithm. So the invariant of the algorithm is saying, so read this invariant once more. At the kth iteration, what it is trying to do? It is taking between any two vertex I and j, if there exists a path, so that path cannot include any vertex whose index is more than k, except the two endpoints I and j. If such a path exists, so mind this time is not the number of edges which we are looking for. In the previous matrix multiplication algorithm, we were looking for the number of edges. Length of the path was important. Here it is not the length which is important. Here it is the index of the vertex is important. Whether that path has gone through the index more than k or not. If it has not gone through an index more than k, that path is okay. Then we said dij is equal to 1. So suppose we do it for k from say 1 to up to n, at the end what we will get? We will get all the possible transitive closure edges, because in any case between any two vertices the paths cannot include any vertex whose index is more than n, if there are n vertices, and we are checking this invariant for each iteration. K is going from 1 to n, so at the end we will get the transitive closure. So once you have understood this, then writing the algorithm is very simple. So let me write the algorithm now. It's only basically 3 loops, very short. So I am assuming that already we have been given the adjacency matrix D, that is dij is equal to 1 if there exists an edge from I to j. I am assuming that. So for k is equal to 1 to n, do. So this is the uppermost iteration, checking whether the vertices are less than equal to k or not. There should be another one, I is equal to 1 to n, do. Another one for j is equal to 1 to n, do. If here is the check. So what is the iteration here? You are doing the kth iteration here between I and j, checking whether there exists a path which goes through the vertices whose indices are less than equal to k. So here you are checking if d so ik is equal to 1. So what does it mean? Dik will have vertices, the path between I to k at this iteration, before this iteration, can have all the vertices less than equal to k minus 1, and in this iteration you are allowed to have the vertex k. So you are checking, so here is I, here is j. What we are checking, whether there is a path between I to k already whose all the vertices are less than equal to k except I and k, and there is a path between k to j whose all the vertices are again less than equal to k minus 1 except k and j. Then there is a path now from I to j whose all vertices have index less than equal to k. So that's the only check you have to do. So if dik is equal to 1 and dkj is equal to 1, then dij is equal to 1. So at the kth iteration, in that case, set up between I and j, there is a path whose vertices have less than equal to k, whose indices. N4, and that's the algorithm. It's so short, so simple, only 3 loops, and there is only one statement within the loop to compute the transitive closure of a graph. Okay, but the concept is not very straightforward. Don't get confused that this ik, this is not the length anymore. We are not looking into the length of the path like the previous one. Here we are looking at the indices of the vertices. The path cannot include any vertex whose indices is greater than k. And that is what precisely this algorithm is doing. So, let us see now how this algorithm will work on our previous graph. So, let me draw that graph again and we will have this example. So, let me draw this graph again. I have 1, 2, 3, 4, 5. So, this is the, suppose this is the graph. We are trying to get a transitive closure. So, first of all, let us see what is the D matrix for this graph. So, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. In this case, I will assume dii is 1. Okay. Since you can reach the vertex I from itself trivial, so I will assume that one. Okay. Here the diagonal elements will remain as 1. So this is 1. I am putting the only the weight matrix. You check whether I am correct or not. This is 1. Between 2 to 4, there is nothing. Between 2 to 3, there is one edge. So this is 1. 3 to 1 is 1. And 3 to 3 by trivially 1. Anything else? No. Then 4 to, there is nothing. So nothing is 1 here. Maybe 4 to 4 only. There is only 1. And what about 5? From 5 I have an edge to 3 and 4 and 5 itself. So this is the adjacency, everything else is 0 basically. So this is the adjacency matrix for this graph given. Now I am going to run the algorithm on this. So initially dij is exactly this. So if you run the algorithm, suppose k is equal to 1. For 1, what are the new edges you will get? I claim it will be between 3 to 4 and 3 to 2. See, now if you include k is equal to 1, there is a path from 3, 1, 4. That path satisfies that invariant. This path includes all vertices whose indices are less than equal to 1. Because it includes only one except the n2. This one, these two ones you should not consider. So between 3 to 4 there is a path which satisfies that invariant. So when k is equal to 1, in this iteration you will see that d31 is 1, d14 is 1 already. So d31 is 1 and d14 is 1. So there must be a path from d34. So d34 should be 1 in this state. So automatically you will have d34. So this will be 1. So let me just, I am just putting k is equal to 1 is the star to indicate the edges which were introduced at this iteration k is equal to 1. I am just introducing the notation star. So this is the one which will be introduced at this case. Not only this, there will be another one 3 to 2, it will find a path at this iteration k is equal to 1, because there is a path now. 3 1 is already there exists, 1 2 exists. So that means between 3 to 2 should be 1. So between 3 to 2 there should be 1 again here. So these are the two, only two which will be set at this iteration k is equal to 1, because there is no other path between two vertices which includes vertices only less than equal to 1. These are the only two. So at this iteration we will get between 3 to 4 and we will get 3 to 2 the edge. Now the next iteration k is equal to 2, I am denoting it as some circle, small circle. You will see So what does it mean? In k is equal to 2, you can have a path with vertices whose indices are less than or equal to 2. So you can see there is only one path this time you will get. Between 1 and 3, now you can have a path. Between 1 and 3, 1, 2, 3, and this is allowed now. Now it is allowed. Between 1 and 3, 1, 2, 3 path is okay. So 1 and 3, now you will have one edge. So at this iteration you will have an edge between 1 and 3, and there will be no other edge which can have less than or equal to 2, which is not set yet. This is the only one at this iteration. Then comes k is equal to 3, I am denoting it with plus. K is equal to 3, there will be many. First look at 2 to 4. 2 to 4, there is a path 2, 3, 1, 4, and this is allowed because k is equal to 3 now. So between 2, 3, 1, 4, so there is a path between 2 to 4 at this iteration. You look now 2, 3, 1, 4, this is getting valid because already you have a path from what? Between 3 to 4 already you have a path because 3, 4 has been set here, and already 2 to 3 there is an edge. So D2 to 3 is already 1, D3 4 is already 1, which means D2 4 should be 1. So that's why you have found out 2 4. There is another one 2 1, there should be another. So 2 1 you can have a path like 2 3 1. This is true because D2 3 is 1, D3 1 is 1. So according to the algorithm, D2 1 should be 1 at this iteration. Then there is another one 5 1, there is 1. Between 5 and 1 there is a path 5 3 1, which is valid because 5 3 is an edge, 3 1 is an edge. So D5 3 is 1, D3 is 1, which means D5 1 is 1. There is another one also D5 2. D5 2 has a path now 5 3 1 2. And how is it computed? Because already you have computed D3 2 is 1. D3 2 is 1 is here. Already you have computed. And D5 3 is also 1 because there is an edge. So D5 2 is also 1. So these are the edges which will be set. So let me just put it here. 2 to 4, there will be 1, which is plus. 2 to 1, 1. 5 to 1, there is 1. Then 5 to 2, there is 1. So this will be set at when k is equal to 3. So next iteration k is equal to 4, you will see for k is equal to 4 there is no change. Nothing will be set now, so there is no change. Because there cannot be any path, every path must terminate in 4. 4 cannot be included in between the way the graph is drawn. So that's why no change. K5, next iteration, again you will see there is no change. And the algorithm terminates. So now you have got a new matrix which is the transitive closure of the graph. You have got a new matrix which represents another graph, and that graph is nothing but the transitive closure of this graph. So this is an algorithm by which you can find the transitive closure of a graph. You must have seen this transitive closure in discrete structure class, where you need to compute sometimes the transitive closure of a graph. So here is an algorithm how can you compute the transitive closure of graphs. So what is the complexity of this algorithm? Definitely it is order n cube because there are 3 loops, each one is running n times. So this is a very simple algorithm which can compute the transitive closure of a graph. Now let me see, we have computed only the transitive closure of a graph. Suppose we want to compute the all pair shortest path. We can have the same strategy now. What do we have to do? Instead of checking whether dik is equal to 1 and dkj is equal to 1, what you do, you just add the values now. dik plus dkj, add that value. So you have got a new value between dij, and check whether dij previous value is less than or greater than equal to this new computed value. If it is, update it. So what is the invariant now? Invariant is you are maintaining at the kth iteration the shortest path between I and j, which includes only the vertices whose indices are less than equal to k except I and j. This is the invariant now. So the same algorithm works only with the change of this one line. So I am going to write now. So what is the invariant now? Invariant, let me write down the invariant first so that nobody forgets. At the kth iteration, compute the length of the shortest path from I to j that contains only nodes less than equal to k. Only nodes less than equal to k means whose indices are less than equal to k, excluding I and j. So this is the invariant which we will maintain, and we have already seen what to do. So what is the algorithm? First, your new matrix D is set with the weight matrix W. W must have been given to you. This is a representation of the graph. So again we have for k is equal to 1 to n do, for I is equal to 1 to n do, for j is equal to 1 to n do. Here is the change, only change. If dik plus dkj is less than already set value dij, between di and j there must have been some other values, because initially if there is no path it will be set now equal to infinity. If there is no path, now it will be set not to 0, you have to set it to infinity, because otherwise this check will not be valid. So dik plus dkj is less than dij, then you update the value of dij. Dij becomes dik plus dkj. And if and for so this, and you can see this does not care about whether the weights are negative, positive or anything. For any weight this should work. This is such a simple algorithm. And how much time does it take now? Again order n. So you can, on the same graph, if you put some weights on the edges, you can run this algorithm and check how it is computing the shortest path matrix, all pair shortest path, how it is setting the values for the matrix D. It's the same iteration, only thing is the change is here. Okay. So this time the metric is not whether there is a connection or not, now it is the length of the path. And actually this has a flavor of dynamic programming. This is nothing but table lookup. You are putting the values in a table. dik is smaller than dij. You are breaking into dik and dkj, which you have already computed, and you have put it into a table. This is just like a dynamic programming with a different breakup. Here you are using k as the indices of the vertex. But this is just the flavor of dynamic programming. So that's it. That is the all pair shortest path. We have seen 3 algorithms, and this is the best if you consider all possibilities. Now since we have a time in this lecture, what I will do now, I will go through the other algorithm of minimum spanning tree computation. We have seen only one algorithm for minimum spanning tree, which is called the Prim's algorithm. but there is another algorithm for constructing the minimum spanning tree, which is called the Kruskal's algorithm. So that's what I'll just give you the algorithm today, and in the next class I'll continue on this, because this Kruskal's algorithm need some sophisticated data structure for certain operations, which we will see later. So now I'm going to tell you Kruskal's algorithm for minimum spanning tree. Algorithm for MST. You recall, for minimum spanning tree the general framework was we have to compute a safe edge. What was the safe edge? This is a minimum weight edge which crosses a cut. If you take that edge, guarantee that you are taking only those edges, you know ultimately you will be computing a minimum spanning tree of the given graph. That we have already seen. And Kruskal's algorithm does also the same thing. The algorithm maintains two basic data structures. So what are the data structure? One is a priority queue, which I will call again PQ, and another we will see, this is the one which we will see later, which this data structure maintains a set system. What is a set system? Basically it maintains a set of some objects, a set of sets. The objects are sets again. So it's a set of sets. So we'll see how to maintain this one later. So this is a set system C for the vertices. So what does it mean? Set system C for the vertices means we'll see that the vertices will be partitioned into several sets. So that this one include all those sets. It's a set of vertices. Now initially, so this is the initialization of the algorithm. So I'm going to write the algorithm now straight. PQ initially is empty. Okay. Then what do you do for each edge UV in the edge set E, do an insert operation, insert UV in the priority queue. And what is the priority of the edge UV? Its weight. Using the weight of UV, you insert it into the priority queue PQ. So that's the initialization. And what is the initialization for the set system C? Initially, each set has only a single vertex V. So it's a set of vertices such that V belongs to V. So each set is a singleton set initially. Each vertex is a set itself. So C is a set of all those sets. Now algorithm proceeds like this. It takes and extract the minimum from the priority queue PQ and checks whether that edge is safe or not. First of all, it checks whether that edge joins two different sets or not. The sets C maintains will be nothing but the small trees. As the algorithm proceeds, the trees will be joined together, merged together to form a larger tree. So when you extract the minimum from the priority queue, first you check whether that edge is connecting two different trees or not. If it is connecting two different trees, you take it. If it is not connecting two different trees, if it is connecting two vertices which are in the same tree for the time being, then you discard that edge. So go on doing it until unless you have only a single tree. So that's the algorithm does. So initially the edge set A is empty, while the cardinality of the edge set A is less than n minus 1. When you have already extracted n minus 1 edges, that means you are done, because you know a spanning tree has at most, not at most, exactly n minus 1 edges. So while A less than n minus 1, do UV is equal to extract mean. extract mean from PQ. Find two sets U and V, two different sets in C. C is a set system. So find the two sets such that U belongs to the set U and V belongs to the set V. So basically you have got the two vertices of the edge which has been extracted from the priority queue, the minimum weightage. Now you check its two vertices, to which set these two vertices belong, and get those two sets. So let U and V be those two sets. Now you have to check whether the U and V are the same set or not. If they are the same set, you discard this edge. If they are not, you include this edge. So just the next check. If U not equal to V, then A is equal to A union UV. Otherwise, U is equal to U. Sorry, not only that, then you also change the set now. If U and V are different, and since you have included the edge UV, then you make the set U and V the same set. So U becomes U union V. So this is the union, and this is U, big U. And remove V from C. End if. And this is the Kurzweil's algorithm. Now we can see I have not told you two things here. First of all, how to maintain this set system now. The sets will have some names, otherwise how will you find out which are the two sets U and V? They should have some name. Each set should have a name in C. So when you first you will take a vertex U, and there should be an algorithm which will give us the name of the set which contains U, and also the name of the set V which contains V, and then you should be checking whether these two names are same or not. That is this check, U not equal to V. So sets should have names. Not only so, this data structure should allow not only to maintain the sets, it should allow merging of two sets into a single set. So what will happen? Two sets with different names will have the same name now. So there should be a data structure for C, which I am not explaining here now. There are many implementations which we will see in the next class, how to implement this set system C such that these two operations, find and this is called the merge or union. So how you can maintain the sets such that these two operations, union and find, can be done efficiently. Because this, if I ask you what is the complexity of this algorithm, you would not be able to tell me until unless you know how much time this find takes, how much time this union takes. And this is a very well known problem called the union find problem. So come up with a data structure where you will maintain a set of sets, and which will allow this find operation. Given an element, tell me which set does it belong to. This is the find operation. This is something like a search. And given two sets, merge the two sets into a single one. That is the union operation. So these two operations have to be executed efficiently, and we will see different data structure how these two operations can be executed efficiently, and depending on that we will analyze this algorithm in the next class. So that is Kurzweil's algorithm. Kurzweil's algorithm actually initially sort all the edges with respect to edge weights. This is actually done by this PQ when you are putting the edges in the priority queue, and when you are extracting next here. So there is a sorting, implicit sorting along the edges. So already you cannot avoid the complexity of, if there are m edges, you cannot avoid m log m or m log n. You cannot avoid that. If there are m edges, you have to use m log n complexity at least to sort this, because you are anyway extract mean, you will take log n, and how many extract mean? This time you will be doing edges you are doing the extracting. This time is not the vertices which you are extracting, it the edges which you are extracting. That you cannot avoid. So we will see in the next class what is the actual complexity.